the chapter Haloalkanes and Haloarenes. These are halogen derivatives of hydrocarbons. The halogen derivatives of hydrocarbons. As we know, the hydrocarbons, the source of hydrocarbons is petroleum oil. During the refining of petroleum oil, the giant molecules of hydrocarbons are broken down into smaller molecules, which upon separation into molecules of different size, which are known as fractions. Each fraction is a mixture of hydrocarbon molecules of almost same size, same molecular size. We have getting what is that variety of hydrocarbon molecules, numerous hydrocarbon molecules from the petroleum source. Some of the hydrocarbons, the molecular structures are written over here. Look at this. These are hydrocarbon molecules of different atom structures, which are produced by just a chemical combination of carbon and hydrogen. Only by the chemical combination of two atoms, two elements, carbon and hydrogen. These two elements produces numerous hydrocarbons, variety of hydrocarbon molecules. What is the reason for this? Reason is a remarkable property of the carbon atom. What is that remarkable property? Carbon has a property as a tetravalent and catenation. What is meant by tetravalent? Tetravalent means each carbon atom in the molecule has a tendency of forming four chemical bonds. Every carbon atom in the molecule has a tendency, has four chemical bonds. The meaning of catenation, it is self-linking of same atoms. Self-linking of same atoms, linking through chemical bonds. That is self-linking of same atoms into, it is a chain of carbon atoms, maybe linear or branch. That is an outstanding property. It is unusual, which we cannot see in other elements. So other elements we don't expect this kind of variety of molecules. The carbon make variety of molecules. This is unusual characteristics of the carbon atom. Just because of this catenation and tetravalent, carbon and hydrogen make numerous molecules of hydrocarbon molecules. Some of the structures of hydrocarbon molecules are written here. Here, look at this. This molecule has 5 carbon atoms connected by hydrogen atoms. Look at the molecular structure. Each carbon has a tetravalent, 4 chemical bonds. But each hydrogen has monovalent. Hydrogen atom has a tendency of forming only one chemical bond. That is why the right structure, hydrogen is only one bond, carbon has 4 chemical bonds. Look at the structures, molecular structures. Writing this molecular structure is a laborious process. When you look at this molecule now, the carbon, 4 chemical bonds. The carbon with this carbon is chemical bond and remaining with hydrogen, that is CH3. This carbon connected by this side carbon, this side. 2 chemical bonds with other adjacent carbon atoms remaining are hydrogen. This by 3 adjacent carbon atoms. 1, 2, 3. Remaining is hydrogen, that is other. That is side chain, that is CH3. That is ending CH3. So all the bonds between the carbon is single bond, but in this case there is one double bond, that is one sigma bond, one pi bond. So this is of this carbon. This carbon, look at the carbon. Already with 2 chemical bonds with other carbon atom, 1 chemical bond with adjacent carbon atom, remaining bond with hydrogen. 4 chemical bonds, 1, 2, 3, 4, line represent. So this must be CH. Look at this molecule, the carbon contains triple bond, 2 pi bonds, 1 single bond. So like this also molecules we have. So this carbon should not have hydrogen because 3 bonds and 1 bond. 3 bonds with this adjacent carbon, remaining 1 bond. Valence is satisfied. This valence is satisfied. No H, no H. Here valence 1, remaining are 3. Valence 1, remaining are 3. That is CH2. One important point I need to stress upon. We need to write the structure of the organic compound hydrocarbon while specifying the chemical reactions. So writing the structure like this, that is a big structure, branch structure, or a lengthy structure, is a laborious process. Just to avoid the complexity, we are using symbols which represent the molecular structure of the hydrocarbons. What are those symbols? The symbols are lines and vertices. The symbols are simply lines and vertices without indicating the symbol of carbon and hydrogen. That is an easy way of writing the molecular structure of hydrocarbons, because variety of structure, bigger structure, smaller structure. Look at this symbol. What does the symbol like this? 2 lines with vertex and ending line with this. If you like vertex like this, there is a carbon atom connected by this chemical bond, these 2 are adjacent. The ending is always carbon. Line ending always carbon. Vertex is always carbon. This vertex carbon is here, and 2 chemical bonds with adjacent carbon atoms. Remaining 2 hydrogen atoms must be there. Those bonds are not indicated. So this point says CH2. This vertex is CH2. This ending line is CH3 because 1 bond is with adjacent carbon CH3. Remaining bonds are 3 hydrogen atoms. So every end of the line represents CH3, CH2. This is propane. And the molecular structure, this is same as this. I will written here that is a molecular structure like this in a simplified form. Look this. The line end always represents CH3, that is this bond carbon with CH3. Here CH3 is there. This vertex means this carbon with H2, CH2. This vertex with this carbon, already 3 chemical bonds. 1, 2, 3 with additional carbon atom. So either you can write upside or downside, doesn't matter. CH3. That is C with 3 bonds already, 1 more bond with hydrogen. That is CH. This vertex must be CH. This end is CH3. That is CH3. So look at that. It is easy. This is easier way. Line with simply vertices. That is, you are using these symbols to represent the structure of the organic molecules. What is this? Similarly, extend this. Ending is CH3, CH2, CH2. Here C, already 3 chemical bonds here. CH, here CH2, CH3. That's side chain. CH2, CH3. That is the molecule. Here CH3, here CH like this. 2 bonds and 1 bond, 5 bond with this carbon atom. 3 bonds already there, remaining with hydrogen. So CH here the vertex CH it has. This vertex has CH, this vertex has CH2, this vertex has CH, 3 chemical bonds, CH3, CH3. Every line ending represents CH3 with one single line. This is CH3, CH2. Here this vertex is C because 3 chemical bonds this side, 1 chemical bond here, 4 chemical bond completely satisfied. This end is CH because 3 bonds with carbon remaining with hydrogen, CH. That is 3 triple bond or alkyne, alkene. These are linear chain, open chain. When you come to closed chain, cyclic molecule like this. So this is the same as this. So written carbon here now, this different orientation because with this you can molecule can have any different orientation. Same structure. Here in this cyclic, what is that? Is not open chain. The chain close like this. Vertex with already 2 lines, carbon atoms, CH2, CH2, CH2. Here C. 3 bonds are there, remaining with 1 hydrogen. End is CH3 always like this. This is CH. This is CH3, CH2, CH2, CH2. Same compound with double bond. CH2, CH2. What is that? CH. 3 bonds with CH. CH. This is the cyclic compounds of higher order. 6 carbon atoms. That is CH2 vertex, CH2, 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 CH2. Cyclohexane. Same compound with single bond, that is double bond. CH, CH, CH2, 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 CH2. They same compound with side chain. CH3, here C, already 4 bonds, 1, 2, 3 line. Must be C only. CH2, CH, CH2, CH2. So this is the easiest way of representing the structure of the molecules. Contains only hydrogen and carbon. If the molecule contains any other atom other than carbon and hydrogen, what is the way of representation? That symbol must be specified. Here, chlorine element, chlorine atom is connected by chemical bond to this carbon atom. This carbon atom. That is CH3, CH, already 3 bonds, with 1 bond is chlorine. CH, Cl, that is CH2, CH3. Here CH3, CH2, here carbon with 2 bonds with carbon atom and other bond with oxygen of the OH. CH here. Here bond showing that is connected to other element, oxygen, but this hydrogen is not bonded to carbon, it is bonded to this oxygen atom. That must be shown. The entire group should be shown over here. In this molecular structure, this is CH3 ending, this vortex is CH, CH, CH2, this is not carbon, nitrogen. So this carbon is connected with the chemical bond with nitrogen. These hydrogen atoms are bonded to this nitrogen, not to this carbon. That's shown. So like this, any other elements other than carbon, hydrogen, those symbols must be specified along with the groups. So that is a way of representation of the molecular structure of hydrocarbons, just to simplify our that is simplify the way of representation. That is one. And look at the structure, very important. The structure is very important. That is similar to the structure CH2, CH2, but here bond is alternate double bonds. That means this vortex already 3 bonds CH, 3 bonds with remember CH. Here this vortex with 3 bonds here. 3 bonds with CH. 3 bonds CH. That is the molecular structure of this hydrocarbon. This is the structure again. CH double bond, C this single bond, C double bond. So carbon atom has, each carbon atom has single bond, double bond, single bond, double bond, single bond with hydrogen atom. This is molecular structure of this. It is called as benzene. So just I want to talk about this benzene. Here the pi bond, double bond is here, triple bond is here. In the organic chain, if there is any pi bond, double bond or triple bond, this bond is reactive bond. Where there is a pi bond, two bonds or three bonds, that bond is a reactive bond, easily undergo chemical reaction. So this molecular structure has three chemical bonds, pi bonds, must have more effective, more reactive, but it is not that reactive, is highly stabilized. The reason for this, if you write this fashion of the structure, this is same fashion. This, look at this, there is no difference. But in alternate fashion, in different positions. Pi bond is here, single bond. Here pi bond changes. Single bond becomes pi bond, single bond becomes double bond becomes single bond. In this alternate fashion. Because of this change in ability, what is that? This molecular structure, alternate single and double bond. This pi bond, what is that? Is not localized. Here the pi bond is localized. Localized, the electrons of the bond, the pair of electrons of the bond remains what is localized, present over here only. There is no displacement. Here the pi bonds are not localized, keep moving because of this, what is alternate position. These pi bonds, all these pi bonds are keep moving, changing this into this. Pi bonds are keep moving in the molecular orbits. That is, any movement of the electron by a bonding electron that is not reactive, that is bonding electron cannot be attacked by any reagent because flowing, moving. So that is the reason that these three chemical bonds are not reactive, it is stabilized. This stabilization is not due to delocalization of the bond called resonance. This has assumes what is that a greater degree of stability. It is what is that? It is reverse of what is expected. So this kind of organic molecule form a special chapter. It is called as benzene or arenes. So we have numerous compounds with what is that? Replacing hydrogen with other side chains. That is hydrocarbons, aromatic hydrocarbons. So entirely it is compounds belongs to aromatic hydrocarbons or arenes. So because of this, what is that? The molecule benzene has what is that? Extra stability because of delocalization of the reactive chemical bonds. Delocalization, not that reactive. So that is what symbolizes the symbolic representation. That is the symbolic representation of what is the structure of the organic molecules. Now come to the chapter Haloalkanes and Haloarenes. What are them? Look at that. It is RH. If any one of the hydrogen atoms of these compounds or this compound or this molecule is replaced by the halogen atoms, any one of the halogen atoms. You know halogen atoms are, there are 4 halogen atoms: fluorine, chlorine, bromine, iodine. That is represented by X symbol. If any one of the hydrogen atom replaced by this atom, it becomes what is that? Haloalkanes and Haloarenes. If the hydrogen atom of these molecules replaced by halogen atoms, they becomes haloarenes. If the hydrogen atom of this compound, this arene compound, here this hydrogen CH is there, any one of the hydrogen or 2 hydrogen or 3 hydrogens replaced by the halogen atom, it becomes haloarenes. Haloarenes. That is haloalkanes, haloarenes. And one more symbol using R. That means except this one, the showing the carbon is hydrogen. This bond is always with the carbon, one of the carbon atoms, and remaining structure is same as molecular the remaining structure of the molecule remains same. So altogether the entire molecule we easily use as an R, a reference symbol by R. Whether it is any other remaining structure of the organic molecule, that is R is our. So that is haloarenes and haloalkanes. And after the chemical bond formation, that is chemical bond with the carbon only, that is structure inside the structure of R. Here there is all other structures. Chemical bond between carbon and chlorine, carbon, Cl, carbon, chlorine, carbon and hydrogen. Look at the chemical bond, you need to study the chemical bond. The property of chlorine, okay, the size of the atom, what is that, increases in this way. That is the smallest size of the atom, highest size of the atom. And this atom element has more electronegativity. That is the least electronegativity. What is electronegativity? Electronegativity means after forming chemical bond, the bonding electrons are attracted more towards itself than this. Bonding electrons are attracted by both this atom and this atom, but more attraction towards this, less attraction towards this. It is called as electronegativity. That is the reason that is more electronegative and the smaller size of atom. You see that in chemistry, atom with a smaller size forming what is that is the bond strength becomes a strong bond usually. And more electronegativity, because of more electronegativity, bond becomes further stable. This is the bond of highest strength. This is the bond of weakest strength. The bond strength, what is that, decreases in this manner. That is reactivity. I am talking about reactivity due to this chemical bond. Highly reactive, less reactive, least reactive, more stable. Yeah, that is the order. So that we need to understand this, because the what is that is the very smallest size of atom and the largest electronegativity. This chemical bond is stronger, not easy to decompose, not easy to break this chemical bond, less reactivity, more reactivity. That is, you need to understand. That is, we have this knowledge of this chemical bond with haloalkanes and haloarenes. Now let us go for classification of these compounds. We have classified these that is halogen derivatives based on two properties. That is the number of halogen atoms present in the molecule. On the basis that you have classified, that is one way. And the carbon atom to which the halogen atom is attached, what type of the carbon atom is? sp3 hybridized or sp square hybridized, sp2 hybridized. On this basis, the halogen derivatives are classified. Here, based on the number of halogen atoms, there is only one halogen, CH3, only single carbon molecule, remaining 3 hydrogen atoms. Only one. It is 2 carbon atoms, one halogen atom, monohalide. That is, of course, cyclic compound, one of the hydrogen is replaced by Cl, only one halogen. Here, this structure side chain, one halogen, CH2, one halogen. And in these compounds, all these compounds contains one halogen atoms, Br. But look at the difference. Here, this carbon, look at this carbon to which halogen atom is attached, are classified into 1 degree, degree 1, 1 degree, 2 degree, 3 degree. That is, the halogen atom is bonded to carbon containing 3 hydrogen atoms. Here, carbon containing 2 hydrogen hydrogen atoms remaining is CH, carbon to other carbon atom. This carbon is called as primary carbon, 1 degree. 2 hydrogen atoms are more than this, is 1 degree. The halogen atom is connected to carbon atom with only one hydrogen atom remaining of the C group to carbon carbon, that is called second degree. With this carbon no hydrogen, this carbon is connected to all the 3 carbon atoms called tertiary carbon or 3 degree. Primary carbon, secondary carbon, tertiary carbon. Same, what is that monohalide with different types we can expect like this. That is one way. Here benzene aromatic compound and containing only one chlorine is alkane, but it is alkane type. Chlorine is not connected to carbon of the benzene directly, but aromatic, but is not, what is that, halohalation, not a haloarene. If halogen atom connected to directly carbon of the benzene, it becomes haloarene. But benzene is the aromatic compound, but not in aromatic compound because of the presence of this, but is not haloarene. Is haloalkane. That is the example. Next, on the basis of the 2 halogen atoms, 2 chlorine atoms connected to same carbon atom, it is called as geminal. This is called as geminal. And 2 chlorine atoms, halogen atoms connected to adjacent carbon atoms, it is called vicinal. There is classification. 2 atoms are there, halogen atoms, the same atoms, they are adjacent atoms. For vicinal, it is called geminal. Trihalide, that is, here the compound is familiar, chloroform, carbon connected to 3 chlorine atom hydrogen, 4 chemical bonds. It must be fluoroform, bromoform, iodoform. 3 halogen atoms. Here 4 halogen atoms, of course, that is tetra, Cl, Fe. I told you, when you find the chemical bond like this, here also 3 F bonds are there. These molecules becomes highly stable because that is stronger bond, not be decomposed. If they enter into the environment by leakage, organic compounds, this will not get decomposed, but these will get decomposed because of weak chemical bond. Decomposed by natural action, leaking into either atmospheric air or water like this. These molecules will not undergo not decomposable, remain there in the atmosphere for a longer time. These 2 molecules are greenhouse, very high greenhouse gases. They can absorb the heat more and emit the heat. Very quickly, what is that? Produces what is that? Greenhouse effect, high temperature. So causes more temperature in its surroundings, that is greenhouse gases. And this, of course, remain there in the atmosphere a longer time. These 2 can whatever is that? Gradually what is that? Move up in the atmosphere, reach the upper atmospheric level, where what is this? This compound will not have any effect on the ozone because this chemical bond contains only chlorine. But this is stronger, but this is weak. By the action of UV rays, what is that? Dissociated, it produces free radical, chlorine free radical. This chlorine free radical will act on ozone, O3 combined, and decompose. That is, ozone to be decomposed by UV radiation will be leaking through to reach the surface of Earth. That is why the compounds like this are dangerous. That is, ozone layer will have effect on the ozone layer, making ozone holes leaking. That is, some UV rays are leaking through because of this interference of these molecules to ozone. But this will not interfere because not containing chlorine, but causing greenhouse. But this will cause both greenhouse effect and ozone problem. That is tetrahalide like this. All the chlorine atoms, carbon tetrachloride. The compound is familiar. Four carbon atoms. That is four halogen atoms. So this is of the basis of number of halogen atoms connected to this. Present in the molecule. In the other type, what is what? sp3 sp square carbon. Look at that. Which carbon atoms are sp3 hybridization? The carbon with all single bonds are sp3 hybridization. To which carbon the halogen chlorine is attached to this? That is called sp3. Here also all single bonds, but this carbon is not in the ring. What is that inside the ring? It is outside the ring. All single bonds, sp3. Here benzene is there, of course. This carbon with single bonds, maybe H, CH3, H or CH2. It is benzyl like this. This benzene group, benzyl Cl. So these carbon atoms are sp3 hybridized. This is one class of halide. Aromatic, of course, here aliphatic. This is aliphatic in nature, but aromatic, haloarenes. So this class is called as, what is that? The carbon halomere. This is the halogen, the carbon atom to which the X attached is sp3 hybridized. What is sp square? Here the halogen atom is connected to carbon, which is sp square, sp2. That is double bond. Carbon with double bond means sp2 hybridized. To this carbon, this halogen is connected. It is sp square. This is a different halogen. Here also, the carbon with double bond connected to carbon with double bond. Here same as sp2. And this compounds, that is called alkyl compounds, called vinylic. It is vinyl group. It is vinyl group. Vinylic compounds. But this is of course aromatic. But this carbon is sp2 hybridized. Connected to this. This is a class belongs to sp square halogen atom. It is called haloarenes. Here haloalkanes. Vinylic. These are sp square, sp2 hybridized. And this another compound, but double bond is here, but halogen is not connected to carbon with double bond. Halogen is connected to carbon with single bond, spq. Here carbon is sp3 hybridized, carbon is sp3 hybridized. Here carbon is sp3 hybridized. Single bonds, 3 another hydrogen here. sp3 hybridized. So this belongs to sp3 hybridized. It is called allylic. Allylic means the halogen connected to carbon, not to this directly double bond. Carbon which is adjacent double bond. It is called allylic. This is also allylic. This is also allylic. Single bond carbon with that single bond double bond. Carbon is single bond double bond. Carbon is single bond double bond. Next alpha beta like this. Alpha beta. So this is called allylic halides. So on the basis of this, that is that hybridization of carbon to which halogen attached, you can classify it into there is two types. This is one type, whether haloarene or haloalkanes. The other type, haloarenes, haloalkane, is sp square, spq. Next, to the benzene molecule, we have now two halogen of Br. Here dihalide positions are different. Trihalide, here monohalide with other groups are there. All of them are haloarenes. Here sp square, sp2. So a halogen atom attached to the benzene ring is always sp2 hybridized. Any halogen atom connected to carbon of the benzene, that is connected to carbon, halogen derivative of benzene is always sp2. Every carbon is sp2 hybridized. Haloarenes. So this is a kind of classes. What is that? On the basis of number of atoms of halogen, we are classifying this as like this. On the basis of the carbon to which X attached, it may be sp cube, sp square. We have classified these halides as like this. This is a classification of the haloalkanes and haloarenes.